Hi everyone, welcome to my YouTube channel again, and today it is going to be about the beginning of fabrication of semiconductor. So to start with, we're going to learn about some wafer. So there are a lot of kinds of wafer these days, such as 4-inch, 6-inch, 8-inch, or 16-inch or 12-inch wafers, and from 450 millimeter wafers, we call it is a 450 millimeter. However, below the 450 millimeter, we call it by putting a name with an inch, with a unit of inch. So, as you can see here, it looks like a grid, and we call one part of the grid a die. So in one die, we put some electric circuits in it, and in the wafer, there are a lot of circuits in there. So if we make a larger wafer, it means there will be much more circuits developed in here. Um, so you might think why we don't use a much bigger wafer, such as 450 millimeter wafer. Um, to make a conclusion, 450 millimeter wafers are hard to control when we fabricate the wafer, and also it is very hard to move the wafers. Of course, the cost problem happens for the companies. So as as the years went on, a lot of wafers were developed from starting from 100 millimeter wafers till the 450 millimeter wafers. So there are four driving force for the device to scale down the device. We call it PPAC, which stands for power, performance, area, and cost. So why are we doing the scaling down? Of course, we are doing scaling down to make the device performance much more better. And also, if we make the device smaller, there are a lot of benefits. However, because of some benefits, there are some side effects, such as short channel effects that we learned previous class. So let me now just talk about um, um, the scaling down. Um, we scale down the device by making one side 0 0.7. So if we calculate the area, 0 0.7 times 0 0.7 is approximately 0 0.5 uh, times smaller. So if we make the one side 0 0.7, the area will be approximately 0 0.5 times scaling down. As I told you about the PPAC, let's look at it more detailedly. So about the area, when we scale down the device, the area decreases by 50%, which means, as we know from the Ohm's law, if the area gets smaller, then the density of electricity gets higher. Just by knowing by J equals QMUE, um, we can know that the electricity density of electricity gets higher, and which means the resistance gets lower, and by tau equals to RC, um, the tau will get lower because of the resistance got lower. As we put that if as we put the C to the constant, then of course the frequency will get higher, which means it gets the better performance. So as I told you about the PPAC, if we make the area smaller, of course the performance will increase just about like 25%. And of course the power dissipation, we made the area smaller and there were less resistance. The power will also decrease, indicated about minus 20%. And of course, we made the device smaller, then the cost will decrease. As you can see here, about 50%. So this is just a scale showing when we made the gate length smaller by developing by years. It indicates that about the PPAC. However, in between 2000 and 2010, between them, it was very hard to scale down the device. The scaling down development were getting very slow. However, we tried to scale down. Every people tried to scale down the device, and in conclusion, 2000 after 2010, we are still making the device scaling down. So this is just supplementary about the power dissipation. P equals to C VD square F. And as I told you, when we scale down the device, the frequency went higher. And because of the frequency gets higher, the power dissipation got higher. So how can we make the power dissipation lower? If we make because F frequency and VD square, we cannot change them. The only way to lower the power dissipation is to make the capacitance decrease. How we make the capacitance to decrease is we need to use another caps, not C-aux cap. We cannot use the oxide cap because the oxide cap is for the gate and the channel coupling, the coupling of gate and channel. So we have to use another parasitic cap. We need to decrease the another parasitic cap to lower the capacitance. So these days we use such as TCAN models to make a process design kit. When we just many engineers order to the circuit engineers to not make problems such as short channel effects. As you can see here, around the gap they use the spacer, just aluminum and gate source, gate between gate and drain. They made it short to make the interface cut off. So as you can see, they have different colors to indicate that another sources were used. The doping are different, so they use different color so that the circuit designer can understand. So we call this PDK, stands for Process Design Kit. It's called a design rule. In the next class, we are going to get more deep in about the lithography. Lithography is a very important part for the fabrication in semiconductor. Just let me give you a little quick review about the lithography. So it is just engraving, such as we engrave some words into the book, or we just make a stamp. It's just the same mechanism. But the important thing of lithography is that we want to make a picture to the part that we only want, which means if we don't want to make a word into the left corner, we must not make it to the left corner. We only want to make it to the right corner. So this is a very important thing to do, and we are going to learn much more deeply in the next class. Thank you for listening to my review, and I hope you enjoyed it. Thank you.